Hello everyone and welcome back. This video will serve as an introduction for working with timers on the STM32 and will provide several different examples on how to use them. So what is a timer? A timer is essentially just a counter that increments by 1 with each clock pulse. So if your clock is running at 10 megahertz, then your counter will count up 10 million times per second. However, counters have a maximum value associated with them. Upon reaching this max value, the counter will roll over and restart back to 0. For an 8-bit counter, the max value is 255. For 16 bits, it's 65,500, and for 32 bits, it's over 4 billion. On the STM32, almost all of the timers are 16 bits. So, if we were using a 100 megahertz clock, the max time we could count up to is 655 microseconds, which isn't very useful. Fortunately, we could fix this by using a prescaler. The prescaler sits between the clock and the timer. Its job is to divide the frequency of the clock to a lower value. So, for instance, if the main clock is at 100 megahertz, we can use a prescaler of 10,000 to reduce the counting speed to 10 kilohertz. So now, with the addition of a prescaler, we can count all the way up to 6.5 seconds. In addition to each timer prescaler, there is another prescaler which resides within the clock configuration. This is the APB prescaler. The figure you see now represents the entire clock tree for our timers. Note, there are two different APB prescalers. On the STM32G4, the first APB prescaler, APB1, feeds timers 2 through 7. The second APB prescaler, APB2, feeds timers 1, 8, 20, 15, 16, and 17, for a total of 12 different timers. These 12 timers each have their own prescaler and their own max value. However, they share the APB prescaler as shown in this figure, so keep that in mind. ST Micro breaks these 12 timers down into 3 basic categories: advanced control, general purpose, and basic. I'm not going to go deep into the differences between these 3, but do know that the advanced control and general purpose timers are multi-channel and that they support advanced features like PWM. If you're looking to control an external pin, these 2 categories are where you should start. Basic timers, on the other hand, don't directly interface with any pins or support any advanced features. However, they are simple to use and work with. They are great for timing, literally just measuring time and driving interrupts. Finally, before we move to the examples, I want to give an overview about some of the definitions. The max counter value, otherwise known as the counter period, is commonly referred to as the auto reload register, or ARR for short. As mentioned before, for almost all timers, the ARR is a 16-bit register. The prescaler, which is commonly abbreviated to PSC, is also a 16-bit register, so both have a max value of about 65,500. Most importantly, the hardware will add 1 to both of these values. So, if you were to enter a prescaler value of 0, the hardware isn't going to try to divide the clock by 0, it's going to divide it by 1. Likewise, if you enter the value of 1, it will divide it by 2. Therefore, when entering the counter period and prescaler into the cube IDE, take your desired value and subtract 1. So, if you wanted a prescaler value of 100, enter 100 minus 1. Lastly, this slide summarizes the equations that control the timers. Note that the value of the auto reload register and prescaler are incremented by 1 in these equations. The first example I will show is measuring execution time. A common task we will need to do, especially when performing real-time processing, is to measure the length of time it takes for blocks of our code or functions to run. It's through these measurements that we can optimize and quantify the performance of our code. The easiest way to measure execution time is by using a basic timer. We can record the value of the counter before and after we run our code, and by comparing the difference, we can calculate the elapsed time. Notably, by using the values of the clock and the prescaler, we can find the elapsed time in seconds. Equation 2 provides this formula. For this example, I'm going to measure the exact time it takes to implement a 50 millisecond delay using the How Delay API. I'm going to configure the hardware such that the counter increments every 10 microseconds, or to rephrase that, a clock frequency of 100 kilohertz. The G4's natural clock speed is set to 170 megahertz, so I will use a prescaler of 1700 minus 1 to do this. Additionally, I'll use a basic timer, timer 6, and set the auto reload register to 10,000 minus 1. Thus, the counter will count up to 100 milliseconds, then reset. Lastly, I'm going to use 3 different functions for this example. How delay to implement the delay, how time base start, this is what tells our timer to begin counting. If we don't run this, the timer will just sit at 0, and how time get counter. Note the 2 underscores at the start of this function. This function returns the current value of the counter. Now, we can shift to the IDE and begin our project. In the Cube IDE, start a new project, select your board, give your project a name, and initialize all the peripherals in their default mode. Now, within the hardware configuration perspective, navigate to the Timers tab and select Timer 6. Activate the timer. Within the parameters, enter 1700-1 for the prescaler and 10,000-1 for the counter period. Leave all other parameters as default. Next, we'll check the clock configuration window to make sure that the APB1 timer clocks are set to 170 MHz. Lastly, we will check the Sys tab within the System core and ensure that Debug is set to serial wire. With that verified, we can now generate code and switch to the C perspective. Before we begin writing the code, let's first have a look around our main.c file. We can see the same initialization functions that we saw before in the Blinky demo. We have the system clock config initialization function, which sets the clock up in the configuration we specified in our .ioc file. We have our UART initialization, so we can talk with the ST-Link. And at the bottom, we have the GPIO in it, so we can use GPIO pins if we desire. But now there's also a new initialization function, the timer 6 initialization. Here, we can directly see that timer 6 is getting set up with all the parameters that we chose within the hardware configuration perspective. Notably, if your timers are ever not operating at the correct period or frequency, I would check the values in this initialization function first. Sometimes values don't get saved when you are changing perspectives or updating code. Anyways, for this tutorial on measuring execution time, we will begin in the user code private variables section. In this section, we will define our variables that will store the value of the counter when we start counting, stop counting, and then calculate the difference between the two. Next, since our code only needs to run once, we will enter it in the user code begin to block just above the while loop. The first line of code starts the timer. Then, we will store the current value of the counter in the timer start variable. We will then run our code whose execution time we wish to measure. In this case, it's just the 50 millisecond delay. After that code runs, we will store the new value of the counter in the timer stop variable. Then finally, we will calculate the elapsed time by taking the difference between the two. Now, we can connect our STM board to our computer, build the code, run debug, and switch perspectives. Now that we are in the debug perspective, we can select Live Expressions in the top right corner. Here, we will enter in our timer variables, specifically time start, stop, and delta. Now, we will click Resume and let the chip run. We can now observe that the values for our variables have been populated. Notably, we can see that our execution time is 50.95 milliseconds, which is interesting as it implies that the delay function adds an almost entire millisecond of unintended extra delay. We will now turn our attention to implementing delays without the use of blocking functions. Up until this point, if you wanted to blink an LED or control any peripheral at a specific time interval, you had to use a HAL delay API. This is a problem, as the processor has to halt the execution of any code until the delay is over. Fortunately, we can avoid this through the use of timers. To implement a delay, we will first evaluate the current value of the counter. Then, we will continuously check the counter's value until the difference between the newest value and the first value we sampled is equal to our desired delay. Once this is true, we will blink the LED and then reset the counter back to 0. For this example, I'm going to have the counter increment every 1 millisecond and reset every 2 seconds. To do this, I'll set the APB1 prescaler to 4, the timer 6 prescaler to 42500 minus 1, and the auto reload register to 2000 minus 1. Do note, our counter resets every 2 seconds, therefore the max delay the counter supports is 2 seconds. There are 4 functions that drive this example. The first 2 are the same functions we used in the previous example to start the timer and get the counter value. The third is the API to toggle our LED on and off. And the last is how we will write a value to the counter. In this case, we will be resetting the counter back to 0. Now, let's open a new project in the IDE and set all peripherals to their default mode. In the clock configuration window, we will first look to the APB1 prescaler. You may notice that there's actually a frequency multiplier located behind the APB prescaler. As soon as we start adjusting the prescaler's value, the frequency multiplier will increase to 2. Therefore, to get our desired clock frequency of 42.5 MHz, we will set the APB1 prescaler to divide by 8 so that the timer clocks will be at the correct value. Next, we will return to the pinout and configuration window and choose timer 6 from the timers tab. Now I'll activate the timer and enter in our prescaler and auto reload register values. Now we can generate code and change perspectives. Within the main.c file, we will begin at the user code private variables block. Here, we will define our timer start and value variables. Next, in the user code begin to block, we will start our timer and record the value of the counter, which will more than likely be 0 as the counter has just started. Finally, in the user code begin 3 block of the while loop, we will add our code to check for the elapsed time. First, we will get the most up-to-date value of the counter. Then, we will evaluate the difference between this and our starting value. If this difference is greater than or equal to the desired delay value, in this case 1500 milliseconds, we will toggle the LED and reset the counter. Now, we can again connect our STM to the computer, build, and then run the code. We can now observe that the LED on the board is toggling to a new state every 1.5 seconds. One of the primary purposes of timers is to drive interrupts. Specifically, we can make use of a period elapsed interrupt, which is called when the counter resets. Regardless of what the processor is doing or the code it is executing, when the interrupt is triggered, the processor will shift its attention to the interrupt callback and the code within it. For this example, we will use an API similar to before to start our timer. Note that this one has the letters IT in it to tell the processor that we will be using interrupts. You can think of the interrupt callback as simply a function that runs whenever the interrupt is called. Therefore, for our purposes, we will toggle the LED on and off each time the callback runs. Lastly, regardless of the amount of timers that you are using, they all share the same callback function. Therefore, within our callback, we will add an if statement to verify that our timer was in fact the one to trigger the interrupt. Just like before, I will choose an APB1 prescaler of 4, a timer 6 prescaler of 42,500 minus 1, and an auto reload register of 1000 minus 1. Thus, the counter will reset and trigger our interrupt once every second. Now we can open the Cube IDE and set up our project just as we have done before. For this example, the setup is identical to the last, with the exception that the CCR is now 1000 minus 1. Additionally, under the Timer 6 configuration, navigate to the NVIC Settings tab. Select the checkbox to enable Timer 6 global interrupts. We can now generate the code and switch perspectives. Now, within the user code begin to block, we can place our function to start timer 6 and interrupts. Next, we will navigate to the very bottom of the file to user code begin 4. This is where we will place our callback function. Now we can run the code. While using an interrupt to blink an LED may seem like overkill, it is a good demonstration of their function. In future tutorials, we will use timer interrupts to drive peripherals like ADCs and DACs at precise time increments. Lastly, the final example will cover PWM. PWM is implemented through the use of a CCR register. This is essentially just a comparator. By default, the output is high, but when the value of the counter rises above the value in the CCR register, the output will be pulled low. Then, when the counter resets, the output is pulled high again. By changing the value of the CCR register, we can control our duty cycle, which is simply represented by the value of the CCR over the ARR. Additionally, our PWM frequency is just the inverse of the period. On the STM32, the hardware is set up such that each of the timers, excluding the basic ones, has 4 channels which can interact with GPIO pins. Notably, all 4 channels of one timer share the same prescaler and auto reload register, but they have different CCR registers. So, if we were to use one timer to drive PWM to 2 different channels, both signals would have the same frequency and would count at the same speed, but their duty cycles could vary. For this example, I'm going to use pin PC8, which is located on the top right of my board. I'm doing this so I can grab the pin easily with my oscilloscope probe. This pin corresponds to channel 3 of timer 3. I will use the default APB1 prescaler of 1. I'll set the prescaler to 170-1 so that our timer is driven at 1 MHz. Additionally, I will set the auto reload register to 1000-1 so the period is 1 milliseconds or the PWM frequency is 1 kHz. The code for PWM is really simple. All we need to do is first start our timer using the PWM start API. Then, we need to write to our channel's CCR register. Since we are using channel 3, that's CCR3, and that's it. Note that unlike the other examples, For PWM, the CCR register is controlled in software, which allows us to change the duty cycle as our code is running. Now, we will open the IDE and create a new project for PWM. As always, all peripherals will be initialized in their default mode. First, we will navigate to Timer 3 within the Timers menu. We'll choose the internal clock for the clock source, and under the Channel 3 drop-down menu, we'll select PWM generation on Channel 3. Note that some pins on the STM32 have multiple timer channels assigned to them. For instance, when we chose Channel 3 of Timer 3, the IDE default selected pin PB0 in the bottom center. We do not want this. Therefore, we will reset this pin state and select our correct pin of pin PC8. Next, we can enter in our values for our prescaler and our auto reload register. Next, we can generate code and switch perspectives. Now, within the user code begin to block, we can enter our 2 lines of code to start PWM. Now, we can run the code and program our board. I'll now hook up an oscilloscope to pin PC8 at the top right corner of the board. With it connected, we can now observe the PWM pulse, operating at the correct frequency of 1 kHz and duty cycle of 50%. Lastly, to show how easy it is to adjust the duty cycle on the fly, I'm going to use the built-in push button on the Nucleo. When the button is pushed, the duty cycle will change to 50%, else it will be 30%. Now, if I enter this code within the while loop and run the program, we can observe this function in action. Now on the oscilloscope, we can see our PWM signal with its 30% duty cycle. And if I now push down on the push button, the duty cycle will change to 50%. And that's it. Thanks everyone for watching, and stay tuned for more videos on the STM32G4.